Dieter is a senior research director at NVIDIA. He is a professor at University of Washington since 2000. Dieter's work has received many best paper awards in robotics, AI, and computer vision. He got a Pioneer in Robotics award. And, just to, see the span of things that Dieter has done. So in the late 90s, early 2000s, Dieter was working on probabilistic robotics. And the book that he wrote was a standard book for many people. Then, around the same time, he had these museum robots, going around and, studying those museum robots. Then in the late 2010s, or like around 2010, 2011, there was this big surge of depth cameras. Kinect came out, and Dieter was really at the forefront of, using these depth cameras and connecting it with a lot of manipulation tasks at the point. Then, more recently, Clipport, if you have heard about that paper, right, where they were connecting, vision and language together. And now I guess everyone is talking about foundation models. And Dieter's talk is going to be leading the effort on foundation models for manipulation skills. So, I'm super excited, Dieter, that you are with us. Please welcome Dieter once more. And please take it away.
Thank you so much for the overly kind introduction. So the museum project, I was a student and a postdoc, so I wasn't anyway in the leadership position there. But yeah, that was my introduction to robotics a while ago. I guess I got many people also because I sneaked in this word foundation into my talk, because that's what everybody seems to be talking about these days. But you should have in mind, I already put there's two caveats. There's a word in front of that, toward, which means we're clearly nowhere there. And I also wouldn't dare to call it foundational, it's foundational skills in robotics, because I think in robotics we kind of have maybe a different perspective of some of these models that we want to build that are extremely capable. The talk I'm going to present and the topics are going to be mostly work that we've done at NVIDIA, but several of the pieces also were done in collaboration, for example, with my students at UW, and of course, everything was very much driven by interns that we had in the NVIDIA lab. So, of course, right now everybody's talking about these generative AI, large language models, and how powerful they are, and that they're going to solve many problems in AI. And I think it's really fair to say that the progress that we've seen in, let's say, language models, vision models, and I'll call them LVMs just kind of jointly, it's these language and vision models, has been really astonishing, right? If we go back just a year, they were clearly nowhere near where they are right now, and it seems like every month things progress dramatically. And we, of course, as roboticists, have to ask ourselves, okay, what kind of role can we play in this? And when we look at what contributes mostly, I think, at least that's my view here, on the success of these stories is, first of all, they have just huge amounts of data on which these models can be trained. And this is not just arbitrary data, but it's kind of data that comes from an appropriate, let's say, distribution. And then there are also on the let's say, deep learning side, there are new kind of models that seem to be capable to digest kind of almost any amount of data and generate very capable outputs from that data that then, even though the model might initially not have any strong structure in it, but they seem to extract that kind of structure from the data and use it for future prediction kind of tasks. So we're thinking here about transformers, diffusion kind of model, but also this notion of prompting, where you have these models where you can, instead of, let's say, retraining them on new tasks or doing some kind of, let's say, meta-learning style work, you just give them some examples of what you want them to do as an input, and without retraining, they suddenly can generate output that is very appropriate given the input, right? So for example, generating Python code and things like that. And for the training, my view is actually coming, let's say, from a robotics perspective. It seems like what works extremely well. It's not that they do, let's say, unsupervised learning. It's some form of self-supervised learning or weakly supervised learning, where especially also, say, on the language model, I would almost call it behavior cloning. So in robotics, where we have examples of actions a robot should perform, and in behavior cloning, you take these examples that come from a hopefully some kind of knowledgeable expert. They don't have to be perfect, but they have to be reasonably good. And then you have a history of inputs, and you're trying to predict what, let's say, what the expert would do next, something like that. And that is, in a sense, what I think many of these language models are doing, right? They get in sequences of words, and then they predict what the next words would look like. Okay, so in that sense, I see there's some analogy to behavior cloning here. And then what we also see, of course, I think that was especially used for GPT-4 and ChatGPT, is that then there's some human feedback, additional feedback coming into these models, and then they do some additional reinforcement learning, but mostly for fine-tuning the models, right? But the bulk of stuff is really doing behavior cloning. So the advantage of these models is then also that the kind of data that they have access to, the internet with all the text that people put there, it's not just a random collection of words, right? It are words that, and sequence of words that come out of the meaning that humans put into them and have in their mind when they wrote them. So it's not just an arbitrary distribution of stuff. Okay? And until, I think, very recently, as roboticists, we were always able to say, oh, well, that has nothing to do with me because they can't do this, they can't do that. And especially, we were always able to say, like, on the visual, the early work on the visual understanding, we always could say, well, but they don't really have 3D understanding, and there's no compositionality, and they're not general enough, and they're not precise enough. And these systems don't have any notion of, let's say, intuitive physics, and their temporal reasoning is very weak. But it feels almost like whichever of these remarks you might make, a month later, it's kind of becoming almost obsolete. So I think now we are really at a level with the most recent iterations where it seems like the reasoning capabilities, and I'm not talking about the long-term planning, but in general, the reasoning capability and the understanding of these models that they seem to have, even though they're just trained on this text data, for example, is that they are really getting closer and closer to true abstract understanding even of what's going on in the physical world. And then at the same time, now we could say, well, that's all still just high-level reasoning, and we roboticists are all about control. But then at the same time, there are all the deep reinforcement learning people coming at us, and they solve the control problems. So the big question for us as roboticists is, so what are we going to do now, right? Are we going to just say, well, it was a fun time, let's pack up and go home? Or is there still something that is not solved by these models, right? Because the problem is sometimes also the general public, they don't understand the details and things like that, right? For them, it seems like that these models are on the brink of also fully solving the general AI problems, and they're going to solve all the robotics problems. And even if there's something left for us, then maybe whether there are any insights we can take from the true success stories of these models, right? So in order to look at this, I just want to, for context, give some of the examples of what's going on there, let's say, in the realm of training robots for kind of deep learning manipulation kind of tasks. Here are some examples in the upper row. It's mostly what's called this embodied AI research community, where it's about developing 3D simulation that resemble the real world with real layouts of rooms and houses. The limitation of this work is often that the low-level physics, like especially with respect to manipulation, the low-level context physics and things like that are often kind of abstracted away, which makes it hard actually to transfer the results that we learn in these environments to the real world. On the lower row, you see some work that is more focused on manipulation. But my sense is actually that that even those works, typically they aim at benchmarking progress in control and machine learning, but they're the focus is not so much on, let's say, the sim to real transfer, which means it would be nice if you could just go into some of these environments and show that if you're really good on a certain task in this environment, you can take that solution, put it on your real robot, and it's going to work, right? I think we all agree as roboticists that would be really nice. But at this point, I think that is rarely actually the effort, the real focus of the work there. Even though, for example, the work in Hao Su's team at UCSD, the many skill work, and also some of the work going on at NVIDIA is aiming at using more realistic physics simulation. But again, sim to real is not the key focus of this line of work. And then there's some other related work where actually the focus is stronger on, okay, we want to train things that actually work in the real world. In the upper row, you see some examples where people look at, okay, can we train skills in simulation so that they transfer to the real world? And the first team that actually showed this in the dexterous manipulation realm was OpenAI, where they showed, you might remember the shadow hand, doing like really cool dexterous manipulation tasks. We did some follow-up works at NVIDIA, and of course, Pulkit's work is fitting really well into this domain as well, where again, the idea is we train something in simulation, even though it's a non-trivial context-rich task, and train it in a way so that it transfers to the real world. There's also like a benchmarking system, the TriFinger. Factory is some recent work we did at NVIDIA where it's more about industrial-specific tasks, and we have now some results where actually we are able to transfer those also to the real world. Another line of thought is given more on the second row, where the idea is if we want to train robots to succeed in the real world, we have to train them in the real world. The data has to come from the real world rather than simulation. So I think the larger scale effort is clearly the work that's been going on at Google with the ARM farm, where they put many manipulators in front of certain settings where the robot does, for example, picking up objects out of a bin. And for their more recent work, where it's about also opening drawers, they built this, you can see this actually over here, this setup where they obviously put together various of these cabinets and then train the robots on these cabinets. One thing to notice is that a lot of this training is done using teleoperation, so a lot of human effort actually involved in that. And then here on the right, there's some effort that is focusing more on also how can we leverage large-scale data to train, let's say, rich representations that we can then use, for example, for a reinforcement learning agent to train it on these representations. So this is closely related to kind of the visual pre-training that we see with mass autoencoders and things like that. There's different directions, especially also using like large-scale data set, YouTube videos, or this Ego4D kind of videos that was a very large effort by Meta AI and their collaborators, where they also put in a lot of work on semantically labeling all these. I think so far, when we think about what are the successes, the sim to real gives very good results, but I think typically the things that are being trained are very, very highly specific skills. So it's not kind of a general skill that works in any environment or so, right? And then on the lower side, the real world data, I think one of the key issues here, of course, it's a huge effort to collect that kind of data. And also, if you want to adapt your data, if you want to train it for a different robot and different environments, then of course, recollecting this kind of data is almost not possible. The final piece here, and that brings me back also to kind of the first slide, is some work on that is focusing more on using these language model-based, these transformers that we've seen here for, let's say, robotics kind of task. The first one was by DeepMind, the Gato, and we did Pulkit mentioned the clipboard work that Mohit, my student, did, where the idea is we want to train a single transformer model to solve many or multiple different tasks, and we're using also, for example, additional input to specify what tasks the system should actually perform. So it's kind of these multitask models. Weimar is a work that actually expanded that notion of prompting, so that you can give even a demonstration could become a prompt for the system, and then it replicates that demonstration. And Also, the RT1 system by Google, you might have seen that, where the robot is doing manipulation tasks in this kitchen environment, is also kind of trained as a multitask transformer that gets as input images and just outputs low-level controls for the manipulator. But again, this relied very heavily on all these demonstrations that they had to collect. And even more recently, we see some of this work that is really kind of directly trying to leverage these large language models for higher level reasoning and planning in robotics. Especially Google has been very active on that. There's also work that came here out of MIT. We did some work, ProcPrompt, where we see how we can prompt one of these language models to generate Python code that then can be executed on a robot. The main observation for all of these models is that while they might be doing very impressive work on the higher level reasoning side, but they still all depend on someone generating these skills that they can then execute. So all they do is they do the high level reasoning, and then they assume I can call a skill that, for example, says like open the door or something like that. So from a robotics perspective, if we want to leverage these things really in robotics, one thing that would be good for us to develop would be robust skills that can connect to these large language models. So to summarize this kind of high-level thoughts, I believe that these language vision models, they will have very significant impact on how we do reasoning in robotics, and also they're going to really help on the visual, perceptual understanding. At the same time, I don't think they're just going to simply solve for us the low-level or the physical reasoning control problems, just because I think the language data doesn't really provide that very well. Now, thinking about the skills that are missing from these models, it seems like, and I think Leslie might agree, we just talked about that, we've been working on these skills for a long time, robot manipulation, right? And we don't have anything out there where, for example, my dream would always be like someone you can just download a model that gives you a whatever pick up object skill or open door skill or something like that, and it just works on your robot, right? So even though we always feel like we're close, but something like that is just not available, right? And that is what I think as a robotics community we should think about in context of these foundational capabilities, foundational manipulation skills for robotics that are very broadly applicable across research labs and even hardware. So my takeaway from all this kind of observing these large vision models over the last few months is really, I hypothesize, I just say that if we can generate vast amounts of robot manipulation data from which we can do behavior cloning, then I think we can really maybe train transformer-style models or so, foundational manipulation skills, so that they can possibly operate robustly in the real world across many different settings, different objects, and different environments. That is kind of would be my goal, and the thought behind is really that these transformer models, if you can get them enough data, they seem to be, it feels like almost infinitely capable, which they are not. I know, and we all know, but still, I have no idea what the limits are at this point. So now where do we get that data from is, of course, the key question. And I think doing so in the real world, the advantage is you don't have this sim-to-real gap, but I think it's just not going to scale. It's just the effort is too large. But I think recent advances that we've seen in simulation will make it able to hopefully generate the kinds of data and the solutions based on which we can do behavior cloning, and hopefully that will then transfer to the real world. So in mostly the next two sections of the talk, I want to give you some examples from the research we've done in the lab on, especially in the first section where we've used simulation to train kind of robot manipulation capabilities. And then I'll get back to kind of how we can go from what we have right now towards this notion of maybe really establishing these foundational manipulation skills that are very capable and robust. Okay, so the first part is what I would call object-centric manipulation. So last time I visited, I don't know how long it's been, 20 years? No, I'm afraid it was on, was it 4 years? Or I think, yeah. Last time it was all about, like I talked about 3D object models and how we do manipulation with known models. So in the rest of it, nothing that we're doing relies on models in the real world. So it's all kind of model-free. But still, we want to reason about objects, even without, let's say, explicit 3D shape models. Okay? So let's look at one example task here. Imagine here's our little robot. It's looking at the scene. On the right side, you see the camera view. And the robot, again, none of these objects are known to the robot. And as the user, you would say, hey, get me that object, right? And in order to do that, you can imagine what the robot has to do, of course, is it has to be somehow able to kind of segment the scene into different objects. That seems to be a fundamental capabilities. And then it has to reason about, okay, how could I actually pick up one of these objects? And another thing that can be very useful to reason about is just collisions, right? Like what object will I collide with if I move in a certain way and things like that. Okay? So it seems like segmentation and graph generation and this collision checking seem to be very fundamental capabilities. And again, if we talk about this segmentation, there's this inherent notion of that it's crucial to reason about objects at the object level in a scene. Okay, so first, based on that motivation, we did a lot of work on what's called unseen object instance segmentation, where you have objects on a table or somewhere, and you're trying to segment them into individual objects. Given that I've already been talking for a while here, I see, I'll skip any details here. But the idea is that especially the most recent ones is, let's assume you can generate training data of objects being segmented, and what these systems, the two on the right do is mostly they do contrastive learning, where you learn to associate pixels that belong to the same objects. They are mapped to a feature representation that is also similar to each other. And pixels that are on different objects, they should be separated in the feature space. That's this notion of this contrastive learning. The most recent work, the object seeker on the right, does actually something a little bit more, where it tries to, let's say you have multiple images that might contain the same object. Then you're trying to also assign the pixels of that object across images to the same kind of area in the feature space, okay? So that you're not just segmenting a scene, but you also have a notion of similarity of objects across different views, okay? And I'll show you later how we can actually use it. But right now we're using it just for simulation, for segmentation. This is the training data we're using here. This is all done in simulation. It's using NVIDIA Replicator to generate these scenes and then the visuals. The nice thing about simulation is, of course, you get all these segmentation masks, everything for free. I'm sure, I guess by now, half of the room have seen the SAM work, Meta AI, segment anything. And yeah, it's of course awesome. And they trained it on 1 billion images, and that were semi-automatic labeled. So I think it's super useful, super impressive. We tried it on we just looked at it on some of our images, and it still tends to over-segment, and our system is trained to give you really kind of a full segmentation of the objects. But I think ultimately, of course, yeah, you want to use these very large pre-trained models so you don't have to do another segmentation work yourself. So now that we can segment a scene, here's just some examples where the second on the left, that's kind of the most recent results we're getting. So you can see that this is actually a pretty nice segmentation, especially of the objects that we care about manipulating here. And the robot was intentionally left out of also from the training data. But you can see that it's actually doing a pretty good job. And that is purely RGB-based segmentation. It's not even using depth information. Okay? And the other two on the right, this is prior work. So we're doing better. Here's one mistake here where the two fruit juice bottles are kind of segmented together, so it's not perfect, obviously, but that's also not trivial in this case. Here's another scene. So we're doing pretty well on segmentation, and again, fully trained on simulated data. The next thing we want to do is now we want to pick up an object. right? Like how do we train a robot to pick up objects? The good thing is in physics simulation, let's assume you have a database of 3D object shapes, meshes, and this is from the ShapeNet. And what you do is the really brute force approach is you take an object model and you just randomly guess gripper poses relative to that object, okay, which is 3D translation and 3D orientation. And then for each gripper pose that you guessed, you just run it through a physics simulator where you say, okay, I'm going to close the gripper and I'm going to shake it. And if it was a good grasp, the object is going to stay within the gripper, and otherwise it's just going to fly away. Okay? The nice thing is on GPU, you can do this in parallel on many objects and many different grasps. And then what you get out of this for an object here in green are, for example, different grasp poses for the gripper that have a high chance of succeeding on this object. Okay? So now you can do this. We did this here, ShapeNet, on more than 8,000 objects. You can see here on the right, these are the different objects associated with the gripper poses that were successful in the physics simulation. A pretty big data set. You can download it. And now all we have to do is we train a deep network to kind of take as input a view onto an object and generate gripper poses from that distribution that we have in that data set. Okay, and this is, we have different techniques for that, but one of them is, for example, the 6th GraspNet, where the idea is the input to the network is not a complete shape model of the object, but it's just an observed point cloud of the object, because that's what you will see in the real world. That's one of the key advantages, of course, using simulation, because in simulation we can use the full model, but then we can train a network to deal with partial occlusions and things like that. So input is the point cloud, and then we train, in this case, a conditional variational autoencoder that actually can sample grasp poses for the gripper that come from that successful distribution that we have in our data set. Okay? And it turns out that these grasps sometimes cause collisions and things like that because it's still noisy. So we can then have actually another network that takes as input the point cloud of the object and actually a rendered point cloud of the gripper. And all it has to do is to be a discriminator that says, okay, is it going to succeed or not? So for example, if it detects that something is in collision, it can just output like red here or something like, no, that's not going to work. And since it's a deep network, we can actually, it's differentiable, we can actually use that network also to refine the grasps, where we say, how should the robot gripper move in order to increase the probability of success? Okay? And we train that just on this data set with these almost 9,000 objects, and it turns out it works actually pretty well in the real world, out of the box. Okay? So there is no additional fine-tuning with real-world data. The main point here is because it's depth data, and depth data transfers actually reasonably well. So here's just some examples. Again, the nice thing is that the model generates actually multiple possible grasps per object. The one on the lower right, you can see that's an example where it just barely misses it, but we're getting a pretty good success rate. So this is just on a single object, but if we go back to this initial scenario where we try to pick up the coffee cup, is we can do the following, where the input is, again, our RGPD observation. And let's assume we do some segmentation there, and someone says, pick up this object number 3. Again, there's no object models or so involved here. Then what we do is we can kind of extract a small area, the point cloud around that segment. We can feed that into our GraspNet. The GraspNet now is going to generate a bunch of grasps, right, that it learned. And then, in addition, what we're going to do is we're going to have another network that checks which of these grasps are going to be in collision with other objects in the scene. Okay? And it turns out that doing this through a trained network, doing collision checks through a trained network, first, it turns out it's actually faster because we can do many of them in parallel. But the other advantage is that if you train that network on sufficient data, it can actually predict collisions that are occluded, which means if you just do point cloud checking, you're going to say there's no collision here because you can't see it from your viewpoint, but these networks can, of course, learn to predict collisions even in unobserved areas. And then we can go back to our scenario and see how it does. So again, we want to pick up that coffee cup. Now the scene is segmented. This is like the coffee cup, the target segment. We generate grasps, and then the collision checker checks for all the other segments. What is their, let's say, probability of causing that collision? In this case, the highest scored one is the one with the red segment. So again, the network realized that none of the grasps were accessible. So now the simple thing is you can say, well, the red object is in the way. Let me get that out of the way. So we just go back and say, OK, let's redo this, and let's try to move that. We can feed it through the whole pipeline. And the robot detected that, OK, I can grab that. Move it out of the way. And then you just go back to the original scene, let's say, and say, OK, now there's a grasp available, and pick it up. So it seems like, again, even though there's 0, let's say, 3D object models or so involved, but the system already exhibits some kind of reasoning that initially we thought would actually be very difficult, right? But we can design the different components for that. I want to just give you one more example of the most recent work here is, it's this, what I mentioned, this object seeker segmentation. So there, the idea is it's not only segmenting objects in the scene, but you can also input, you can see here on the lower left, you can input an image of the object that you want the system to detect. So it takes the input image of this saucepan, and then it looks in the scene, which is the views are the other two images here, and it's going to give you the segment that belongs to the object that you give as an example. Kind of makes sense, right? And then what we can do is we can just say, OK, we can just tell the robot to pick up the saucepan here. And it works actually pretty robustly, I would say. And then you just say, OK, now get this bowl out of there. And importantly, actually, the motion controller on the robot here, it's using Model Predictive Control, MPPI, and it's using this trained collision checker to rank the rollouts that we're getting through the Model Predictive Controller. And you can see, again, the input is always the upper left image. And these don't have to be images from the same scene. This could even be a product image or something like that, right? They can look pretty different. Let me just give you one more where it's putting something into. So here's, for example, the Coke can. A totally different orientation, but the model can identify it pretty well. And then, again, once we have the segmentation mask, the rest is just grasp generation and motion. All right, so what I wanted to show you here is that we can actually build systems that at least start to be reasonably robust in the real world. And this is purely trained in simulation. There was no additional adaptation we did in the real world. And the approach was really kind of, I call it object-centric, because the notion is really we always deal with objects, right? We say, the first thing is I do, I'm going to segment the scene, that gives me my objects, and then we're going to reason about what I'm going to do with this object, how I'm going to pick it up, and how I'm going to move it. Yeah, Nick?
So very impressive, and you may want to defer my question till the end of the talk. So you said, yes, we can do these things. You're at the, you built very impressive object segmentation, 1.7 million examples of grasps, gives you the ability to learn the grasps. Can I push you to take a position like, is this what we should do as roboticists? Is that we should give up on physics and we should give up on contact models and we should just build as large a data set as possible? Or are there limitations here where there's a role of the classical approaches and physics, et cetera, where we still want?
I'll defer. No, I'll defer till tomorrow or later at the bar or so. You know, maybe it's my age. At this point, the one answer is, I just want this stuff to work finally. At the same time, I must say, there is, for the data generations, we're doing everything. We do all the physics reasoning, and we can do the controllers and everything, right? Of course, yes, we're using them to generate that data, but in the end, all of that is baked in, and we're using the learning techniques to kind of compress that information into something that works in the real world. Doing all these things in the real world, as you know, is just from scratch, is extremely hard, especially based on partial knowledge about the world and things like that, right? Because you have all these occlusions and you don't have shape models. So the approach that I'm mostly talking about today is really this notion of in simulation, we have access to all that privileged data. That privileged data lets us solve tasks that we just can't solve in the real world yet. And then what we have to do is we can use that to generate data on which we can do more or less something like behavior cloning, let's say, right? But the key trick is that that has to be done in a way that it transfers to the real world.
That's a more hopeful answer to your initial question. What is the role of roboticists? Which is that we need to understand the physics and how to do these things in a classical way to generate the training data, but you shouldn't deploy that because it's going to be too slow and brittle, and the learner what gives you the actual operational system.
Yeah. I think there are quite some insights in here, I think, that come from the fact that we are roboticists and we care about doing this in the real world, right? If you look at, again, at many of these examples in the embodied AI, 3D simulators, we as roboticists look at this and immediately say, no, this is not going to transfer to the real world, right? So there has to be quite some care has to be taken to design the simulation environments and everything so that it will transfer to the real world. And this data generation process is non-trivial, I think. Okay. All right, thank you. Next part, and that is going to be just quickly about this work like Clipboard, Perceiver Actor, where the idea is, again, we don't want to explicitly reason about objects, because in some situations that might not even be appropriate, or it might be very difficult, right? So for example, there's always this kind of, whatever, if you have a pile of coffee beans somewhere and you want to move them, what does an object, what does it even mean in that context, right? And Mohit is using this notion, this is kind of the key pieces of his PhD thesis, that we should specify tasks much more at the level of what the robot should do rather than what we want to happen with objects, for example, okay? So it's more driven by actions rather than objects themselves. Of course, one note already, in the end, if you do this sufficiently enough, out of it might come something that can reason about objects, of course, because it might turn out to be necessary to do these actions. Okay, so just briefly, very quickly, like Clipboard, the idea was we want to teach manipulation tasks, and the idea was with Clipboard also kind of leveraging language instruction, language information during the demonstrations. And the inspiration for that comes from two works. The first one was transporter nets that Andy Zhang and his colleagues did. That was at Google, where the idea is you have a top-down view onto a manipulation scene. And again, rather than segmenting the scene and doing things like that, they realized that for these pick-and-place tasks, where a task that can be specified by the robot should put the gripper somewhere and then move it somewhere else and then release it or something like that, I can specify them rather than doing that, let's say, in the 3D XYZ and orientation space. I can specify them directly kind of in the visual input. So I can take the top view image onto the scene, and the task of where I should put the gripper becomes just kind of a heat map over my visual space. Okay? And they showed that with this idea, they can actually learn from very few demonstrations, surprising variety of different tasks, but limited to this 2D top-down view world. The key limitations from our perspective was that the network had no notion about what the task was about, or there was no additional context to these tasks. And therefore, they needed to train a separate network for every single task. Okay, because again, the network couldn't reason about this variability. So then around the same time, what came out was CLIP. And CLIP are these language vision models. This was, I feel like, one of the very first like really big models and surprises also about how capable they are. And the idea of CLIP is it takes images and texts and learn to map images to embeddings that are similar to the embeddings of the text that, for example, describes the image or something like that. So they learn a joint kind of embedding space about image and language. The limitation for with respect to manipulation, we felt like was that it didn't have the kind of pixel level resolution that you sometimes want for manipulation tasks. So Mohit came up with the idea of just combining these two works into a single one, where now we have a network that has a frozen pre-trained clip stream that takes as input image and text, and also kind of a transporter stream that takes care of the precision. And then what he was able to show, that you can suddenly, by taking language into account as well, they were suddenly able to train a single model on many different tasks. Okay, I think this was one of the first examples for this multitask learning for manipulation. Now the key limitation is that it's only like this top-down 2D. So the perceiver actor work is, there was a call last year. The idea here is we want to extend that to full 3D reasoning, which for manipulation means like 3D position and 3D orientation of the gripper. I think in the interest of time, I'm just going to skip details, but the idea is you voxelize your environment into 1 centimeter size voxels, and then you generate tokens that have 5 by 5 centimeter resolution cube, because it's like this 3D space. And then what it learns is it takes as input a voxelized representation of the scene and a language description of what the task is, and then trained on some demonstrations, it learns to output which of those tokens, the 3D voxels, is a good position for the gripper to go next in order to solve that task, and also which 3D orientation it should take on. Let me just give you one example here. For example, if the task is put the tomatoes in the top bin, what the network gets as input is this 3D voxelized space, and the language, put the tomatoes in the top bin, and then what it generates is the pose where the gripper should go next, if you want to put the potatoes in the top bin. The key strength of this work was it can be trained from very few examples, and now the next one is, okay, we feed that now back into the model, and the model based on that input now says, well, the gripper gotta go down. I hope you can see this on the right side. This is always the next gripper pose the system should go to. And now it should retrieve it. The system also outputs whether the gripper should close or open, and whether the system should avoid collisions or not. Here we assume that the motion between those points is handled by just a motion generation system, a controller that can also avoid collisions. Okay, so now tomatoes. And in order to do this, the system really has to learn, like, okay, where is the top bin and things like that. Okay. And just give you some examples. So he did 53 demos in the real world, and then it's able to do all this variety of things. So here you can see the benefit, of course, that it's really 3D, different elevations and things like that. And doing some of these tasks with with an object-based approach, not so trivial, because then you have to say, oh my gosh, now I got a bin detector, or I got to detect the stem of the tomatoes and things like that. So that's, I think, one of the advantages of this more action-driven approach, that you don't need to specify objects themselves. You just tell the robot kind of what it has to do, and the system can learn then what it needs to identify in the scene in order to know where the gripper should go. Okay. Oh, one example here that's actually interesting. So Mohit then just recently, he looked into also kind of, there are these attention maps over this voxel grid, and you can visualize actually how much attention, let's say, the model pays to the different voxels. And here the input, the task is turn the right tab. It turns out it's not so trivial, because to detect where the right tab is, you actually need to know where the faucet? Is it the faucet? Yeah. Where the faucet is, because only that is how you find out whether it's the left or the right tab. Because the faucet can also be in any orientation, and you can see here in this attention map on the right side that it actually pays attention to the top of the faucet and then to the right tab, because it just learns in order to reliably identify that I also need to look at the faucet, for example. Okay, so now if we look at the same thing, like turn the left tab, we get again this attention, but now the attention again, it looks at the faucet, but also in this case, it's on the left tab. So you get some kind of a task-driven recognition, right, of the objects. Oh, and right now, I have noted, but we developed, this is at NVIDIA, we developed kind of a model. The problem with perceiver actor is kind of, it's pretty memory intense. because of this 3D voxelization and training, actually the model might take 2 weeks if you want it to be good on various tasks. Here the idea is rather than using a voxelization, you can represent the task by multiple virtual views into the scene, let's say. The advantage is that then the transformer only needs to reason about 2D views rather than 3D voxelization. And the smart thing is here like how you combine the outputs of these views into something that then really gives you still your 3D position and orientation. Okay? And with this model right now, the success rate is actually even better than Perceiver Actor. But that was not the main goal. The main goal was also getting down in the training time. So we get Perceiver Actor took 16 days to train, for example, and we're now down to 3.3 days. So that's already a progress. And of course, things hopefully will get faster over time. So that's going to be actually the model that we're going to use in the future, moving forward too. Okay, so now I want to go back to these foundational manipulation skills. I hope so far at least I gave you a sense of that, especially with the first part, that simulation, that we are where we can use simulation to actually train models that work in the real world and pretty robustly. I presented 2 kind of ways of looking at that. One is more different components where we say there's segmentation, grasp generation, and collision checking and things like that. And the other approach is more like this action-centric approach where we're using these transformers. And now we're working towards, okay, how can we kind of maybe combine these insights and hopefully get to something that might be useful for hopefully many people. So here's the idea. First of all, it's going to be for object rearrangement. This is Rummy, our new robot. We just got it recently. It's not very pretty. It's Genova Gen 3 arms. It's pretty bulky and everything. But for now, I mean, as a research prototype, it's kind of good enough. And we are still in the stage, because we just got it recently, we're still in the stage where we're very happy if we can move the arm like a centimeter forward and backward. Roboticists know what that means. So this is just, we kind of put it there for the picture, okay? Just, it's not doing that at all yet. But I'm sure next week it will be able to do all of that. So when we talk about these kind of basic manipulation skills, right, where I think the goal is really to enable the whole community to kind of share these so that they work across labs. And if you think about right now, every lab that does manipulation, they kind of almost build their own models from scratch because there's nothing really out there that works well for them. So the goal is maybe to get to something that can be reused. So what we would like to have is, first of all, we want to learn skills that cover many of the aspects of, let's say, rearrangement in these kind of, let's say, cabinet-style, let's say, environments. Could be kitchens, could be hospitals or things like that. The key, of course, we want it to be able to unknown objects. It should also work in unknown environments. It should handle some variation in the kind of manipulation and gripper we are looking at. It should, of course, let's say the assumption is, of course, all parallel short gripper for now, let's say. But hopefully at some point we will have models so that if you have slightly different model or something like that, it's not going to work anymore. So they should be independent of that. And the key piece is, of course, we want this stuff to work in the real world, right? Because otherwise it's not going to help us roboticists. So now the question is, what level should these skills be defined at or specified at? Because that's always one of the problems when you think about a hierarchical, let's say, robot reasoning control system. There's planning, there's a low-level control, and then we always talk about we want to have hierarchies, but nobody really agrees what the hierarchy should look like. And we want these hierarchies, of course, if possible, to just be learned and magically come from the training data, but that's also very difficult. So at this point, I'm totally happy to just specify exactly what I have in mind there, okay? So, but the guiding principle for these skill levels is, again, they should be something that can be used in the context of different kind of reasoning systems. So, for example, if you have a large language models, you should maybe be able to call these skills. But also, if you want to task and motion planning, or even human teleoperation, it might be nice if these skills would be useful, even for a remote controller of these robots. And the intuition of this is related, of course, to Kahneman's. We see this also a lot being talked about in robotics these days. System 1 and 2, where the idea is system 1 are the kind of things that we humans do without, let's say, explicitly thinking about them. It's these kind of automated skills, like when I pick up this object, I don't think about like how I actually did this, right? The magic of humans is, of course, these skills just come up somehow, and we are even able to move things between system 2 and 1. So for example, if you think about learning to drive a car, initially this is a very deliberate, hard process for you, but if you keep on doing it, then you just don't even know anymore what you're doing there, right? So we are obviously able to compile experience into these kind of skills, right? So, but at this point, we only want to focus on the low-level stuff because the language people are going to figure out all the other parts, okay? So let's look at it just kind of to see where we want to go with this level is, let's assume we say like, get my keys there in the left drawer, and we're talking about the drawer down there. Then I think ultimately, of course, depending on where you're coming from, you could say, well, one level to define that skill would be retrieve keys left drawer. That seems, from my perspective, a bit too high level because there's quite some reasoning involved in that, right? You have to think about multi-step stuff and what is left drawer, things like that. An alternative would be, okay, open left drawer skill, but that's also like then you have to first look at which drawer are we talking about. So that also seems to be still involve a bit too much thinking, let's say. I think a very reasonable level would be where you just say, I want to have an open drawer skill, and somehow the context provides of which drawer I'm talking about. Okay, we decided we want to go one level broader, where we just say we want to have a skill where it just say open that thing. Okay, and whether it's a drawer or whether it's that cabinet door up there, it should be the same skill. Okay, so we don't want to. We all know that the definition of task and skills is very broad. So some people define a task to be different if it's picking up a different object. Here we want to have it really broad, where we just say a single task is open, independent of whether it's a drawer or a door. I'm not talking about boxes and things like that at this point. Okay, and at that kind of level, it seems that would be great, right? Because then the robot would just have to still figure out maybe where the handle is and how to open it. But it seems like that is stuff that can be done, hopefully, in an automated way. Similar level of skills would be close, or pick up, retrieve an object from, let's say, a shelf, place. And I'm open simplifying some of the stuff. Like insert, for example, should ultimately also be a skill, right? Just like that. We're working on that in a different context, so I'm not going to mention that here, or also unplug. Right? So if we had that level of skills and they would actually work in many unknown different environments, I think that would be awesome. So the next question is then, what's the interface to this skill? Like if you have your robot, how are you going to call that skill? And for example, you might say, well, I'm using a bounding box detector. Someone else might come with a mask, right, as a context and say open, and here's the mask of the thing. Someone else might prefer just translation, rotation maybe of the handle or something like that. Or you might just ultimately, of course, we all know it's going to be an embedding. But it's not clear at this point, right, what is the right interface for these things. Or someone might just say, that is my specification of opening the drawer. We're just providing you an image of the open drawer. We've seen this in a lot of the DeepRL kind of community. So the level that we decided on is actually a very simple approach, which is kind of pixel-based. And I think ultimately, of course, you would like these skills to be able to be called from any of these interfaces. But we know that this is going to be very hard. So this notion of the clickable world that Charlie Kemp came up with, where the idea is you just have a laser pointer pointing at an object, right? And that idea we can transfer here, where we say, you just say open, and the context for open up here is, for example, a pixel on the object that you want to open. Okay, so it's kind of what we would like to have is kind of a clickable world for robots here. Okay, so that's what we're going to work on first, right? Now, the next big thing, and I'm going to rush through this, is the key thing, how we're going to generate the data for this. Because, as I said, I think one of the key problems in this whole domain is generating sufficient data to train these, for example, transformer models and things like that. And we're going to do all of this in simulation. I'll just give you some examples for where we are right now. So one problem scene synthesizer where we're actually generating these kind of cabinet-style environments. We're taking many of the, it's not ShapeNet, it's PartNet data set, but we can also reshape them and then assemble them into these kitchen environments. The nice thing is we make sure that they all work with physics, with the full physics simulation, so they have all friction and masses that are somewhat realistic. Okay, so, and the format is USD or URDF. I don't want to go in the detail here, but we can generate now with this setup, of course, we can generate whatever an arbitrary number of them because it's procedurally generated. And then we're lucky because Kaylin Garrett is in our lab, who worked with Leslie on Tomas on task and motion planning, and I think he's one of the very best people in the field. And again, because we are in simulated environments, we can just place objects and we can specify tasks. And task and motion planning works actually pretty well because in simulation you have access to all the information. So Kaylin is then going to generate these solutions for us. A caveat, what you'll see is it's not pretty yet, but it's just the very beginning because we just got also this manipulator. But imagine we can then have a task like put these 2 cups somewhere there on the countertop. And obviously the motion of the arms and things like that will require quite some more optimization, but I don't see it as a fundamental limitation. So we can now, again, generate many scenes, many tasks, generate beautiful solutions to them at some point, very soon. And then the next thing is we can also do, of course, we can use the task and motion planning system to automatically generate these key points that a system, for example, perceiver actor needs. Right? You remember perceiver actor was defined by where should the gripper go next. So here you can see in red is the goal point, I think, for the right gripper, and in green for the left. So we can generate demonstrations also annotated with these key points. And if you have, let's say, 1 million of them, which we don't, but hopefully at some point we will, then you can replay them by simulating the camera data that the robot observes in these scenes. For that purpose, we need the scenes to look somewhat more realistic. So for that, we're using a tool by NVIDIA. It's called Replicator. Here's just with some very simple textures, but you can see that we can, of course, then take these scenes and we can render them different ways. We can also put more clutters in them and stuff like that. And another approach we're pursuing is, of course, you've all seen these amazing progress in diffusion models, right? So generative diffusion. So we're also looking into, for example, these are scenes and objects that are textured using diffusion models that are just prompted with a text. So for example, you could prompt it by saying, hey, generate me a kitchen cabinet in the style of a modern European kitchen, which is more colored and things like that. Okay, so you can see here on the left are some examples. These are also then articulated. What's actually an interesting aspect is if you put the texture on these, you need to make sure that the diffusion model doesn't have too much freedom because you don't want it to just generate an arbitrary pretty-looking kitchen. You want it to generate a texture that is consistent with, for example, the door handles and stuff like that. And actually, this works with these techniques now. Okay? So what I'm just showing you is kind of this idea that I'm pretty confident that we can generate actually very large data sets that look somewhat realistic. And then what we're going to do is we have all this data for these different skills, these examples, and then we're just going to train these, for example, 2 lines of approaches. The nice thing is once we have the data, you can just try out different techniques, right? And then feed them into low-level motion policies. And another approach could be, of course, well, we're going to try, right? We'll see what we're going to get. Just feed it all into one big policy. The advantage, again, of this simulation approach is that we can benchmark things and compare things. And for the motion generation, there's a lot of related work we've done in the lab. So I'm actually pretty confident that we get also, for example, much nicer motions out of these techniques than the ones you've seen in the demonstration so far. I'll encourage you to, at some point, maybe read some of these papers. And with that, I'm coming to the end. I think what we've really seen over the last, actually months almost, right? It's scary. We can't even say last years or so. Over the last months is really incredible progress on what the vision and the language community has produced with these generative techniques. I think in robotics, what's really annoying to me, and I want before I retire, I would like to be able to have robots that have manipulation skills that just work across robots, across locations, and in unknown environments. That would be kind of a nice thing to be done. The key question, I think, is at this point, and that is maybe hinting a little bit with the question that also Nick asked. Now, we could argue, well, we just all run a big reinforcement learning agent and it's going to solve all of that. Maybe that's going to work, but our approach at this point is much more leveraging the fact that we are working in simulation environments to generate good examples and then do very large-scale behavior cloning like these successful models have shown they can do. And I think simulation, again, is a very viable path. We can make them look more and more realistic. I think benchmarking is also another key aspect of pro simulation. And the next step, yeah, generate a lot of data, train the models, and see what we get out of them. And I think this whole notion, this pipeline of data generation and training goes clearly beyond just kitchens, right? You could use it for industrial kind of tasks and things like that, and maybe ultimately add more and more skills to this set. And with that, I'll thank you.
Yes, we might have time for 1 or 2 quick questions. Yes.
Thanks for your enlightening talk. So I have a question for the text. Can we get the mic too, please? Thanks for your talk. So I have a question for the text fusion work. So I wonder, when the diffusion model generates different textures, does it also generate different physical properties like stiffness, mass, center of mass,
Yeah.
things that the robot needs to be aware of?
Great question. No, not at all. So at this point, we just say we generate the physics environment, right? And then it's just about the appearance. And the main purpose of that is so that we can train the models on the rendered images so that it looks more realistic for sim-to-real purposes. That's the only reason there. I think, of course, yeah, that would be great if you could generate textures with consistent properties. That would be awesome. And that's or even if you think about maybe deformable objects, right? Like if you would a shape model of a tomato or so, and then even the properties are appropriate. Yeah, so that's a great question, but unfortunately we don't do that at all yet.
Yeah, but thank you.
Thank you.
Any other questions? One last.
Hi, I'm Maria, postdoc here working with Ted and Alberto. One thing that I notice in like a mug picking problem is that every time I see it, it's done just slightly differently. But one thing that I do notice is that more often than not, the mug is picked up, it's pinched from the open position. If there were liquid inside, or if the mug was clean and then needed to be handed to someone, by picking it up from the inside, you are then contaminating the inside of it.
Yeah.
How, I mean, the task was achieved, right? You picked up the mug. But what are your success metrics? Like if you could pick up the mug from a different position, if the mug was really hot and then that heat might damage the gripper, how do you determine what is a good solution versus a just okay solution?
No, that's a great question, and obviously we're not addressing that at this point. At this point, the only thing at this point we just care about is, okay, can I pick it up and put it down without it falling or something like that? But I think ultimately, I totally agree that, of course, the graphs themselves need to be much more task-driven and much more fine-grained. I think some of that we could get out of if for example, in the data generation, right, for example, with task and motion planning, if it can take into account which of the graphs to prefer depending on the longer range task, because right now the skill doesn't have any of that context, right? Then we can also train models that prefer certain graphs in certain contexts. So when I say, for example, these skills, right now the idea is that they are just called with this pixel. I could well imagine that there's additional information that you might provide to the skills. For example, what is the specific task I want to perform with this object? But we haven't done that yet. No, that's a great question. So right now we're just generating all of them just according to the data distribution that we have in the data set, right? You would have to change that data distribution.
Well, I wish we had more time, but time is running out
Yeah,
fast.
sorry.
So, let's thank Dieter once again for the wonderful talk.
Okay.